Okay, then welcome back everyone for the third morning session of the week. And today we'll have two talks over Zoom. And it's my pleasure to introduce Salman Beigi from IPM, who will be talking about the monotonicity of the Neumann entropy under quantum convolutions.
Thank you. Yeah, thank you very much for the introduction and for giving me this opportunity to talk about this work. I'll be talking about monotonicity of Neumann entropy under quantum convolution, and this is a joint work with Rabi, who is a PhD student in Mark Lula's group. Yeah, so let me start with the statement of the quantum entropy power inequality. Suppose rho and sigma are two M-mode bosonic quantum states, and then the entropy of the quantum state is this trace function. And then the entropy power would be essentially the exponential of this entropy when normalized by the number of modes. And the entropy power inequality essentially says that this entropy power is concave under convolution. I will define this convolution and also these bosonic modes and other things later on. But for now, you can think of this convolution as the convolution of the classical random variables. And this quantum entropy power inequality is, of course, the quantum analog of the classical entropy power inequality, which rates of this form. And then there is also a weaker version, which we mostly focus on that one for this slide, which is this linear form of entropy power inequality, which says that the entropy of a quantum state is concave under convolution. Well, these inequalities, especially the weaker one, is tied for Gaussian states, and also this was first conjectured by Sakat Guha in his thesis in 2008, and then the first version, actually both of them, I would say, essentially are proven by Koenig and Smith in 2014, although there was, they didn't bother to state their proofs in the more general form, but it was done later in the same year by Dipal Bamari and Germanet. So let me, again, before giving the definitions, let me give a relation between this entropy power inequality and the quantum central limit theory. So I'm going to use this notation for, so rho box time box plus n is the n-fold convolution of the quantum state itself, which is defined in this form inductively. And again, you should think of it as the n-fold convolution of a random variable with itself. And then the quantum central limit theorem says that if the first moment of a quantum state is zero, then when I take the limit of n going to infinity, this n-fold convolution tends to a Gaussian state. Just like the classical central limit theorem, which says that this normalized summation of IID random variables, when the first moment is said to be zero, it tends to a Gaussian random. And then what we can say about the relation of this quantum central limit theorem and entropy power inequalities comes from this observation that when we fix the second moment or the covariance matrix of the Gaussian of a quantum state, then its entropy gets maximized when the state is Gaussian. So Gaussian states are maximizing the entropy. So essentially, the quantum central limit theorem says that when we take the limit of n going to infinity, this entropy goes to its maximum value because under convolution, the covariance matrix doesn't change. So it goes to the maximum. So what we can say about this maximum, about this entropy using the entropy power inequality, well, if I consider two copies of the n-fold convolution of a quantum state, if I convolve them, of course, I get a 2n convolution of the rho with itself. And then the entropy by the concavity of entropy, I have this inequality, which of course is the same as the entropy of the infill convolution. So what this entropy inequality says that the subsequence of these entropies corresponding to powers of 2 is an increasing sequence. And then the natural question is whether the whole sequence is increasing or not. And again, it was conjecture by Guha in his thesis that the whole sequence is monotone and is increasing. And I should say that this conjecture is, as you can guess, is a quantum analog of a classical conjecture, which was posed by Lieb in 1978, and it was taken about 25 years until its proof, done by Artestein, Ball, Barthy, and Nauer. I know maybe three other proofs of this conjecture in the classical case, and the main result, or I should say a consequence of the main result of our paper is the resolution of this conjecture. So this is the statement of our main result. Suppose rho 1 to rho n are n-mode bosonic states which have finite mean photon numbers. And let's see to be a collection of the subsets of these indexes from 1 to n. And suppose that for any index j, it appears in at most r elements of these subsets in the collection. And then we have this inequality. So on the left-hand side, I have the entropy power of the convolution of the whole states together. And the right-hand side, I have, in some sense, the average of these entropy powers, where the average is over the subsets in the collection of the sets, and then I take the states in that corresponding to that subset, they take the convolution, and then compute the entropy power. Let me consider two particular special cases of this theorem to get what this theorem says in particular. So let's n to be 2, and let's consider this simple collection of sets, so the individual singleton sets. Of course, R is equal to 1 because each element 1 or 2 appears exactly once in this collection. So R is equal to 1. And then if you write down this inequality, we get this thing, which is, of course, the entropy power inequality for the special parameter lambda equal to 1/2. So this theorem is really a generalization of the entropy power inequality when the subsets are assumed to be disjoint. Let me take another example. Let's say all the states are equal. And then let's say my collection of sets is the collection of all subsets of size n-1. There are n of these subsets. And then my R is equal to n-1 because each index appears in n-1 of the n sets. And then if you write down this inequality, this general case, we get this inequality, which was conjectured by Guha, and then so we solve this. Now let me go to the definitions. So for a quantum bosonic mode, my corresponding Hilbert space is this functional space with the O2 inner product. For M modes, I have, of course, the n-fold tensor product of this function space with itself, and then the density matrices are, of course, positive and normalized operators on this space. What is important about this space is that I have this creation and annihilation operators. For 2 modes, for M modes, I have 2m of these operators, which when I think of this particular representation, this creation of these annihilation operators have this particular representation, but this is not really important. What is important is this commutation relation, this bosonic commutation relation. So the operators for different modes commute with each other, and for a single mode, the commutation between the annihilation and creation operator is equal to 1, or I should say identity. So this should be equal, I guess. Yeah. Okay, there's a typo. I talked about Gaussian states. I don't use it that much, But for essentially a Gaussian state is Gaussian. It is a state whose logarithm is quadratic in terms of creation and annihilation operators, and a particular thermal states are. I also have displacement operators in this space. These are unitary operators defined in this form in terms of creation and annihilation operators, and then the expectation of these displacement operators or the wave operators give me the characteristic function. And the importance of the characteristic function is that I can write down any state in terms of these displacement operators and the characteristic function integral form. And the way we should think of this characteristic function is really, again, a quantum analog of the classical characteristic function. So this function e to the itx is well, the displacement operator is the quantum analog of this function e to the itx, whose expectation gives me the characteristic function, and I have a same representation of this for density function. So everything is really analog of the classical. And now the question that I want to answer is, what is the definition of the quantum convolution? To do that, I'll first start with the classical convolution. I have this pair of random variables, x and y, and I know that the convolution of these two random variables, well, when I normalize it with this parameter lambda in this form, has this definition. So the way that I want to think about that is to first think of this pair x and y in some two-dimensional space, and then rotate my coordinate system. So instead of representing x and y, I want to represent it with this pair of random variables, which really comes from the rotation of my original random variables. And then, of course, if I take the marginal over the first random variable, I get this desired convolution. And I want to define a quantum convolution in the same way, and from now on, I'll mostly focus on the single mode case. I assume that m is equal to 1. So this rotation is done by this unitary. The exact form is not really important. What is important is that it really gives me a rotation. So this rotation, so I should think of this annihilation and creation operators as my coordinate system. And what this unitary operator does is to rotate my coordination system corresponding to this parameter, the square root of 1. And then tracing out over the second subsystem gives me the quantum convolution. So I start with two states, rho and sigma. I apply this change of coordination, rotation, and then taking the trace over the second subsystem. And in terms physically, it's just a beam splitter. The convolution comes from the interaction of my two states under a beam splitter with transmissivity parameter lambda, and then tracing out one of the outputs. In terms of characteristic function, it comes from the characteristic function of the convolved state is the multiplication, comes from the multiplication of the characteristic function of the individual states up to some normalization. Again, similar to the concept. And now I can go back to the statement of the main result. I want to pause for a second here so that make sure that everyone now understands the statement of the main result. After that, I'm going to go to the proving of ingredients. So if there is any question or comment about the statement, I'll be happy to hear that. Okay, good. Okay, just to make sure, do you have my voice?
No question.
Okay, good. Okay, so now I'm going to go to the proof ingredients. The first one is the quantum de Bruyn's identity, which is quite a standard in this theory of quantum entropy power inequalities. And the idea, the whole idea comes from the classical case. So this one is quite a standard. The first one, the other three ingredients, I would say, are new in our work. The first three ideas give us a new proof of the quantum entropy power inequality, and then for ingredients will help us to prove this generalized version. Okay, so what's a quantum difference identity? To consider this Link-Blodian operator and then the corresponding semi-group of CPTP maps. And I can perturb my state under the CPTP map. So rho t is the evolution under this this quantum heat semigroup with time parameter t. And the nice thing about this semigroup is that it, in some sense, commutes with the convolution map. If I take the convolution and then take the action of the semigroup, it's the same as first applying the semigroup and then call these states. So that's one nice, good observation about this heat semigroup. And then the second observation is that when I compute the entropy of rho t, in the asymptotic limit, the entropy would behave something like log t. So no matter what my starting state is, asymptotically, its entropy is a constant plus log t. So what does it mean? It means that this at least this weaker linear version of the entropy power inequality is satisfied in the asymptotic. So in order to establish this inequality, I can look at the entropy change for time less than infinity. For that, I can compute the entropy. I won't go through the computations. It's a simple computation. So, but I get an expression of this for A is my annihilation operator, and I should think of this commutator of A and rho essentially as the derivative. So it's really a quantum analog of the derivative. So I compute the overlap of the derivative of rho and the derivative of log of rho. And we know that what's the derivative of log of rho? We have already seen it yesterday, and at least in the talk of about the error exponent. And so we know that the derivative of the log function can be written in terms of this integral representation. So the whole derivative is we realize that it's equal to what is called the KMB Fisher information, quantum Fisher information, which I denoted by I of rho. So this whole observations we had in this slide will show that in order to prove the quantum entropy power inequality, at least this weaker version, it suffices to prove this inequality for in terms of the quantum Fisher information. Okay. So from now on, I'll focus on this inequality for quantum Fisher information. And in order to understand this inequality, we should maybe go back to the classical picture and then see what this quantum Fisher information is about. In the classical case, the Fisher information is the integral of, so let's x to be my random variable with density f of x, and then the Fisher information would be the integral of the derivative squared divided by f itself, which I would like to think about it as the norm squared of this derivative divided by the density function itself. So this thing is usually called the score function of my random variable, and by this norm square, I mean norm squared in terms of this inner product. So if alpha and beta are two functions, the expectation with respect to this random variable of the multiplication, well, alpha bar, the complex conjugate of alpha times beta, the expectation would be the inner product, essentially this integral. So this is an important observation that I can think of this classical Fisher information as a norm square of what is called this score function. And I'm going to do that. Think of quantum Fisher information the same. I just told you that this derivative is replaced with the commutator, with the annihilation operator, and then I should divide it by rho itself, because rho is the quantum analog of this density function. But of course, this division I should make sense of it because I can divide things in the quantum way, in non-quantitative way, in different ways. So to formalize this division, I can use some theory that will be clear in a second. I can start with some function kappa, which I know is operator convex and also is normalized in this way. And then out of this function, I can define this phi function, which is a function of two variables x and y in this way. And this normalization helps me to have this equation phi of x, and x is 1 over x. So I can really think of this phi as division by x. And that's exactly what I'm going to do. If x is our arbitrary operator, I'm going to define x divided by rho as the action of this super operator, which I'm going to define on this operator x. So what is L? L of rho is multiplication by rho from left, and R is multiplication by rho from right. So L and R are two super operators. They commute with each other. So phi of L and R is well defined because I emphasize that L and R commute with each other. So this phi of L and R is a super operator, which I can apply on X, my operator, and I'm going to interpret it as X divided by rho. In the same way, I can think of multiplication by rho in some non-commutative way. I'm going to define the psi function to be 1 over my phi. 1 over phi was essentially division by x, so psi is multiplication by x. So this is the correspondence between phi and psi. And then using the psi operator, I can define my inner product, which is going to be the quantum analog of this inner product that I had over here for the classical case. So here I have this super operator, which I want to think of as multiplication by rho. I act it on my operator x, take the dagger, and then take the overlap with the other operator y, which is going to be my inner product between x and y. And then what is important about this form of inner product, especially by starting from this function kappa with this properties, is that this inner product satisfies the data processing inequality. So you should think of the manifold of all quantum states, and then at each point of the manifold, take the tangent of the space, and I'm going to define an inner product and tangent of the space so that this inner product, this data processing inequality is satisfied. And the whole point of this theory is that these are essentially the only ways of defining this inner product in order to get this data processing inequality. Okay. Yeah, let me now give you some examples. So the first example, this is, okay. So before giving the examples, let me give you the review what we had about the escrow function and what corresponding quantum Fisher information. So escrow function was the division of the derivative of rho by rho, and the derivative comes, and the division comes from this function phi, which is fixed in terms of this function kappa. And then I'm going to define this quantum Fisher information, the general form of quantum Fisher information, as the squared norm of my escrow function, which I can write down in this. Some examples. The first example is this thing. Let's kappa to be, let's say t is equal to 1, equal to 0 for simplicity. So kappa is 1 over x. And then the corresponding psi would be just x. Or if t is non-zero, my psi would be some linear combination of x and y. So, and then the corresponding inner product would be essentially the usual inner product that we can think of. We can think of multiplication of rho from left or not, right, and then take the average of them. So the nice thing about this thing is that this inner product is linear in rho. We can think of other inner products that are not linear in rho, but this choice of function kappa would give me linear inner products, and these are important inner products for me. What about the other one, which we saw in the quantum deep-learning identity, the Kogomori-Bogolyubov Fisher information? It comes from this choice of function couple. I won't go to the details, but what is important is that this really gives me the K and the Fisher information if I go through the same analogy. Define S of rho as the derivative of rho divided by rho in terms of this function phi, and then take the corresponding linear product, and then take this for. Okay. Now let me go back to this function kappa. These are the two conditions that I have before. Let me add a third condition, which is the symmetry condition defined in this form. And what is important is that all of these functions are characterized in this paper by Hiai, Kosaki, Petz, and Ruskai. These are essentially come from the functions that we had for the linear inner products. If I take all of these functions, take some weight over the parameter t, take the integral, I get a function kappa that satisfies these properties. What is important for me is that this matrix division corresponding to this K and B Fisher information that I'm interested in can be written as the matrix division in terms of the simple matrix, simple functions, these things here. And remember, these things correspond to linear inner products. So what it means that, so I was interested in improving this linear inequality in terms of K and B Fisher information. Instead of K and B Fisher information, which is not easy to work with, I can work with these Fisher informations corresponding to this linear inner. If I prove the same inequality for these two Fisher informations, then I can take some integral essentially by like taking some average over some parameter t, and then get my first inequality for the Fisher information. Okay, so that's the second ingredient. For the third ingredient, so far I guess it's now has become clear that I want to think of this Fisher information as the squared norm of some operator, some vector in some Hilbert space. But now I have three of these vectors: the square operator for rho, the square operator for sigma, and the square operator for the convolved state. But these operators live in different spaces. One of them lives in a space for the inner product corresponding to state rho, the other one for sigma, and the third one for the convolved state. The question is that can I somehow put all of these vectors in the same state in the same space in order to compare them with each other? And to answer this question, I can define this lifting map. So I'm going to lift these operators in the same space and then compare their norms to each other. And the lifting is done by this tilde operator, which is defined at this point. So I start with this displacement operator. I define this tilde or this lift in this form. So the tilde lives in the tensor product space. And then, of course, I can do it linearly and define this tilde operator, this lifting for all trace class operators, which can be written as integral over this displacement operator using the characteristic function. I'll define it this way. And the point is, I won't go through the details, but you can really define this tilde operator for all operators, not just trace class operators. So we have this tilde operator, which behaves something like this. And what is nice about this tilde operator is that we have this equation. Well, in the first look, it may seem nasty, but to understand this equation, so this psi is my multiplication operator. Is the same psi that I had before. The way you should think of this operator is that this tilde operator is really the adjoint of the convolution map. So here I have this tilde operator, here I have convolution, So these are really adjoint of each other with respect to the Hilbert-Schmidt inner product. So that's why we have this equation. Also, I would like to emphasize that this equation doesn't hold, for example, for the K and B inner product. It's that it holds only for the linear inner products. Otherwise, that doesn't hold. And that's why we are focusing on linear inner products and turn the proof of the inequality for the KMB Fisher information in terms of this linear Fisher informations. So that's the first observation about this lifting map. The second observation is this important equation. So which says that if I take the derivative of the convolved state up to some normalization factor is the same as taking the derivative of one of the states and then convolve with the other state, which is really the quantum analog of this equation. If I consider this convolution of two functions f and g, take the derivative, it's the same as taking the derivative of one of the functions. And then convolve. So this equation also holds. And now if I put these two observations together, I get this important equation. S of rho is the score function of the state rho. I take its tensor product for the second mode, and then I have this my tilde operator, which lives in the tensor product space. I take the overlap of these two operators with respect to the tensor product weight. And what I get is that the overlap of the operator T with the score function of the convolved state. So I have the same equation here. And now using this equation, it essentially says the following. Let pi be the projection on the space of these tilde operators. So take all of these tilde operator, or I should say that the image of this lifting map, take the pi to be a projection of the closure of this image. And then what this equation says, essentially says that if I take the score operator of my state rho and make a projection on this subspace that I just told you, I essentially get the lifted operator of the score function, the score operator of the convolved state. And of course, the same for the second state. Now, if I put these things together, I get a proof of the entropy power inequality. So what was my Fisher information is the score operator of the convolved state. This tilde map doesn't change the norm. It's easy to verify that. So instead of the score operator, I can consider its lift. And then I can lift, using the equations that I just had, I can write down this lift as either the projection of the first score operator or the projection of the second one, or any linear combination of them. And then it's easy to well, the first step, I remove this projection pi. It doesn't decrease the norm. So I come up with this equation, and then it's easy to verify these two, that these two operators are orthogonal with respect to this projection. So I can use the Pythagorean identity to write this equation, and this is what I wanted to. So as you see, the proof is it's a new proof of the entropy power inequality. I should say that if I do this more carefully, I get the proof of the original, the exponential form of the entropy power inequality. But that's with the simpler case, it's clear from this derivation. As you see, it's nothing but ignoring a projection. The whole proof is this. So what about the proof of the main result? For the main result, which was in terms of the convolution of different subsets of the state. So for that, I have different subsets and like n states and different subsets. For each subset, I have some score operator which lives in a particular space, and then I should consider this projection and so on. So things are complicated. In particular, I should define this lifting map corresponding to the tensor product of the whole states, rho 1 to rho n. And in order to do this analysis, we should decompose this tensor product space in terms of some subspaces that are easier to work with. So to do that, I should consider this conditional expectation operator. It's really the quantum version of the conditional expectation for random variables. And because again I'm working with these linear inner products, I can verify that these conditional expectation operators are mutually commuting, and also they are projections. So they really, I can use these things, these conditional expectation operators, to decompose the space into some solid space. If I take the multiplication of some of these expectation operators and identity minus these operators together, I get some projection, because each of them are projection is the expected conditional expectations, and they commute with each other. So these products are also projections. Also, they decompose the whole identity, the whole space. Okay, so that's the fourth ingredient that comes. The idea really comes from the classical case, a proof of this generalized version by Madiman and Baron. And if we use this fourth idea together with what we had before, we come up with a proof of this this generalized version of the entropy property inequality. So I wrote down the proof in the spatial case that gives Guha's conjecture. I won't go through the whole details. The first step is really using these projections and writing down the tilde operator in terms of the projection of these of the square operator corresponding to the subsets. And then at some point, I should write down this is a new ingredient. I should write down this decomposition, so the projection of these square operators into different subspaces. And then at some point, you should apply this Cauchy-Schwarz inequality. That's where that parameter R appears in the ascendant of the theorem, the races this equalities. Okay, so by this I can I'll stop talking and we'll be happy to answer questions if it's time.
Thank you very much for this beautiful talk. Is there any question, either in the audience or Zoom? No question? Yes.
Hi, thanks for the beautiful talk. So you use these monotone metrics basically to define different Hilbert spaces. Is there a way to directly and explicitly relate the Hilbert spaces that you get?
Well, if your question is whether we can do this directly in terms of this KMB inner product and KMB Fisher information, well, I don't know. I mean, well, of course, we can write down everything in terms of some integral over that parameter T that we had. But a direct proof, no. I mean, we use this linearity of those inner products many times in this proof.
Yeah. My question was more about the general theory related to these monotone metrics, but might also be a bit more too detailed for here. Maybe I just look into the paper.
Yeah.
Any other question? Perhaps one for me as well. So you talked about this decomposition, your last step here. What would you get anything else if you're looking at other conditional expectations rather than these partial traces? Does it give you any?
Yeah. Well, again, I don't know this. I mean, considering this conditional expectation, it really comes from this linear inner products. So probably your question is, or at least the variant of the question would be, what if you consider other conditional expectation with respect to other inner products? Yeah, I don't know. I mean, some parts of the proof really, we really need this conditional, we really need this linearity of inner product. But for this part, no, probably no. And I don't know the answer. I think it's
Combies, may I ask a question, please?
Yes, sure.
Salman, this is Nilanjana here from Cambridge. Thanks very much for this beautiful talk. So you've developed these nice mathematical new tools to prove Guha's conjecture. And so now it seems like a closed story. But do you think there is these mathematical tools that you have developed might have applications elsewhere?
Mhm. Yeah. Hi, Nilanjana. Really nice to hear you. As you probably know, we use part of this theory for the central limit theorem and the optimal rates there. Especially this lifting map is used heavily there too. And also, I should add that this is not really the end of the story. There are other inequalities in terms of entropy that that might be based on this theory. I mean, we are trying to explore this area. In particular, a big open question is in this area is the entropy photon number inequality. We don't know whether we can use this theory for proving that one. It seems to us that we need a new ingredient, maybe beside these things that we have. But yeah, there are several open problems still there that we are exploring.
Thank you.
Okay, so if there is no other question, let's thank the speaker again.
Thank you.